In a normal gun, we fire a projectile using the force of an explosion. So we have some sort of projectile sitting in a barrel, then we blow something up right behind that projectile, maybe some gunpowder or something. That creates an explosion, and the force of the explosion propels the projectile out of the gun at the enemy. Right? That's the idea of a normal gun. The railgun works in a different way. In a railgun, what we are doing is using electromagnetic forces instead to propel our projectile out of the gun. Of course, according to Newton's first law, the acceleration of an object is equal to the force that is applied to this object divided by its mass. In this case, we're trying to accelerate the projectile, so the acceleration of the projectile is equal to the force applied to it divided by the mass of the projectile. And we're trying to generate that force using magnetic fields. So in a railgun, we've got two parallel rails. Okay, this is a schematic drawing. And these rails can basically be seen as wires, electric wires. And they're not connected to each other, but they are both connected to the sides of a power supply. So the first rail is connected to the positive side, and the other rail is connected to the negative side of a power supply. In between these rails, there is a projectile that is made of a conductive material, such as steel, for example. Right? It's a conductive projectile, and it touches these rails, which means that when we turn on the power supply, an electric current will start running from the positive side of the power supply through the first rail into the projectile, then out of the projectile on the other side, into the other rail, and then back to the power supply. So far, so good. Right? This is not too difficult. Now, this is where the magnetic fields come in. Okay, so first of all, I'd like to point out that in this railgun, there are no permanent magnets. Okay, so the projectile is not a magnet. These rails are not magnetic. There are also no coils involved here. It's just these rails that are basically wires with a projectile in between them. That's all there is to it. So first of all, let's take a look at the magnetic field generated by the rails. So of course, when we've got electricity running through a wire or a rail, that creates a magnetic field around this wire. Most people know this. So if I have a wire, like this pen might be a wire, and I have a current running through the wire, we're going to have a magnetic field created around it. Right? That's basically an electromagnet. And we can predict what that magnetic field looks like using something called the right-hand rule for wires. And the right-hand rule for wires specifies the following. If I take my right hand and I align my thumb with the direction of the current in the wire, and I then wrap my fingers around the wire, my fingers represent the direction of the magnetic field. So when the current runs in this direction through the wire, the magnetic field rotates round the wire like this. If the current goes in the opposite direction, I should use this rule because the current goes that way, so my thumb should be pointing in that direction. So now the magnetic field is rotating in the other direction. So let's take a look at what that looks like in our railgun. Right, so in the railgun, we've got a rotating magnetic field around the first rail, and then a rotating field in the opposite direction around the other rail, as you can see. Now that seems not very exciting, but now let's take a look at these rails from the front, right? So let's take a look at these rails as if we're facing them like this, as if they're coming towards us, okay? That's what it looks like, okay? So you can see that we've got these magnetic fields rotating round the rails in opposite directions, of course. Now, let's take a look at this region, okay? Why are we taking a look at this region? Well, because that's where the projectile is. That's what we're interested in, and there's something interesting. If you take a look at the direction of the left magnetic field in this region, you can see that direction looks like this, right? That's the direction of the magnetic field in that point. And the other magnetic field, if we look at that point too, we can see that it's also going in that direction. So we can see that because we are looking at just the region right in between these wires, right in between the rails, effectively the magnetic field is going down. So in the real world, we've got two wires with rotating fields around them, but because we're just interested in that plane in between the rails, effectively we've got a magnetic field that moves down like this. Now let's take a look at what the projectile does in all of this. So the projectile is not a magnet, we just discussed that, but there is a current running through it. And when we have a current, an electric current running through something conductive, in this case a projectile, that is located in a magnetic field, it experiences something called a Lorentz force. So Lorentz force sounds complicated. It basically means that if we have a wire, again, my pen is a wire, with a current running through it, if that wire is located in some external magnetic field, the wire will be pushed in some direction. It will experience some force because it's acting like a small magnet and it's inside a bigger magnetic field. And we can predict this force, we can predict how the wire moves using the left-hand rule. The left-hand rule goes like this. I take my left hand, like so, okay, and I align my fingers with the direction of the current this time. So not my thumb, my fingers represent the direction of the current in the wire. The external magnetic field is coming down into my palm like this. And that means the force that is applied to this wire will act in the direction of my thumb. So now, let's see how this works in the railgun, right? So in the railgun, what we've got is the electric current comes in through the first rail, then it goes through the projectile and back to the power supply. That means we've got a magnetic field effectively going down. We just explained that. That means the field direction is exactly, oh yes, that's right, down into my palm, right? And the current in the projectile is moving along my fingers. And that means the force that is applied to the projectile is in that direction. In other words, the projectile now starts moving out of the gun along these rails. And that's basically how the railgun works. That is how the projectile is launched. And the more electricity we use, the higher the voltages we apply to these rails, the more current we can get running through it, and the bigger these magnetic forces will become, which means the projectile will go faster. Right, brilliant then. Let's use railguns everywhere. It's better for the environment, isn't it, than burning some gunpowder? I mean, I suppose you can run railguns on wind turbines and solar panels. Well, it's not all that good, because railguns are not very practical. They're not very practical for many reasons. First of all, power delivery. Railguns need an awful lot of power. We need to run a massive electric current through these wires. Especially considering that railguns are applied primarily in bigger guns. So we're not talking about rifles and pistols, we're talking about the sort of guns you might put on a ship or a tank, like that sort of gun, and that needs to fire a pretty heavy projectile, which means we need a lot of current, we need a lot of power through these rails to get it working properly. So we need a power delivery system of some sort, which usually consists of a massive bank of capacitors that needs to be charged to get that amount of power. And that's not practical because it takes up lots of space, it requires lots of maintenance. There are just all kinds of practical problems with power delivery systems. And then also the gun itself has a lot of problems. So a railgun experiences, first of all, there is wear, right? There is massive wear on these rails because of friction, and on the projectile, right? Because the projectile, if it wears when it's in the gun, then its shape changes, and if it doesn't have the right shape when it's in the air, then it can get off course. So we need to consider that when designing the projectile. Also, we have extreme heat issues because we have lots of current running through some rails and a projectile. We get lots of heat inside this gun, which can make things melt and burn. We can even get some welding effects going on. I've seen some videos of people trying to make their own railguns where they had two bars with a piece of metal on it, and the piece of metal just shot that way, but then it went, like after 10 centimeters, it welded itself to the rails because it got so hot, because effectively we're doing welding here. So basically there are a lot of reasons why railguns aren't that practical yet in the real world, and so the normal gun still remains more popular. And actually, perhaps that's a good thing, because railguns can be quite destructive weapons. Anyway, whether they're destructive or not, they're interesting, right? They're interesting to talk about, interesting technology. They work on pretty basic principles, but they're very complex devices to design because of all the problems that we just mentioned. Anyway, I hope you've enjoyed this video, and of course, thank you for watching.